All right. Hello, everyone. I'm Luca. I'm a postdoctoral researcher at the Technical University of Denmark in Copenhagen. And today I'm going to talk about stress-based design for 3D concrete printed structural elements, material-efficient structural elements. I'm trained as an architect, but since the beginning almost of my studies, I've been involved in research about 3D printing and in the design and the making of structures with 3D printing before, during, and now after my PhD. The research I'm going to show today is mostly part of my PhD done at the University of Southern Denmark in collaboration with Hyperion Robotics, Weber, and Danish Fibers. All my work starts from the notion that concrete is the most used material on Earth after water. And this material creates large portions of the global emissions, which are accounted to 7 to 8%. And in this sense, what I'm looking at is that the potential of design in improving to improve this issue and reduce the emissions created by the concrete industry. And if you look here, we can see that large portions of these emissions are due to the material itself. So there's a ton of work that needs to be done on the material, but at the same time, there is quite some work that can be done to improve how we design and how we build. So that's where I'm placing my work. And like it was said before very well, there are very ambitious and virtuous uses of 3D concrete printing. However, in the industry, what is being looked at is size and efficiency in production. So building bigger and building faster. However, I don't think that's what is really interesting about 3D printing. What is really interesting is looking at how we can improve and reduce emissions in the process. So the big question is, how do we design for 3D concrete printing to enhance the efficiency and sustainability of concrete structures? And the first challenge is that conventional construction processes are divided in separate boxes in geometry, material and engineering, and in the manufacturing part. However, we need to start thinking in a more intertwined way. So we need to see fabrication, material, and geometry as one process, and 3D concrete printing needs that even more, because all the parameters that defines the geometry are influenced and will influence both the fabrication and how we use the material. So the first thing I've worked on is understanding the material and the fabrication process. So I've worked on developing a fabrication setup, or better, putting different pieces together. And I've been working with an industrial robot very similar to the one we have here, and a feeding pump. And the material we've been using in our research is a mortar more than a cement, which is characterized by small aggregates. And at the same time, we used fibers to avoid cracking, and we also integrated the conventional rebars in the process. So the first experiments we did, some preliminary experiments, were on understanding the early age properties of our material. So how does the material behave as soon as we deposit it? How much weight can we put on it? But we also looked at how the material behaves after printing, and how it behaves in the different directions according to the layer direction. And at the same time, we did the same for the rebars and how the behavior intention worked according to the direction of the print and the position of the rebar. This informed our modeling and the design preview setup. So we wanted to have an accurate prediction of what was going to be printed. And we analyzed, we used the printing speed as a parameter together with the layer height, and we checked how much the width of our print would change at different speeds and height. And as you can see, there are some of these combinations that led to failure or to very, very ugly prints. And we also did the same for the cross sections. So we saw that we had a range in which we could print, a printing window, and we had different parameters and widths we could achieve by controlling accurately this the printing speed and in relation to the height. So this became a tool, a digital tool that we used to control and optimize our prints. So we tested it with some purely geometrical experiment, and by changing the speed, we could achieve a variable width in our print. And we tested this in a more structural application where we try to vary the speed in a column to see how we could achieve some thicker areas for better stiffness. The big case study I've worked on is on horizontal structural elements, on beams, and then on a slab. And this is because 43% in a middle-sized concrete building, 43% of the concrete is being used on our horizontal structures. And back in the 60s, here is a bunch of examples from Pierluigi Nervi. We have been building buildings integrating structural performance to optimize the design of slabs, of ribbed slabs. However, this because of increasing costs in manufacturing and in the workforce, this stopped until new technologies of design and of fabrication allowed to revamp this approach. And especially in academia, there's been a lot of work to use different fabrication approaches to optimize slab elements. Our approach, my approach, was to try to work on a porous beam. So can the strength to weight ratio of a beam be enhanced by introducing porosity in its longitudinal section to reduce the use of material? And by porosity, I mean literally creating voids in my elements. And the first step was to compare a simple grid porous beam with a full beam. So these are one-to-one elements we designed and printed. They are 3 meters long, and they were reinforced with the same amount, the same volume of rebars. And to print the grid beam, we had to come up with a way of optimizing again the toolpath and the amount of material we were employing. And we did that by creating a woven layer structure where each second layer was printed sort of perpendicularly to the previous one. And we had to work on the speed of the robot to reduce the material in the intersections. So here you can see how the color varies because we are changing the speed to adapt to the material we had below. So here you can see one of the first printed specimens that was tested structurally in 3-point bending. And to our surprise, you can see in yellow and brown, that is the porous beam. To our surprise, that already behaved better than the full beam. And looking at purely at the strength to weight ratio, we already achieved a 58% improvement, and we kept, even though it doesn't give us a complete sense of how much we are actually optimizing. We use this parameter as a comparison element, but at the same time we also ran a full life cycle assessment, and we saw that 70% of the average environmental impact was still due to the material, as we saw in the previous in the diagram earlier. But we could also see that 45% there was a reduction of 45% in the environmental impacts in the porous grid beam. But we wanted to look at how we could integrate finite element analysis to improve the way we designed our beam and the way we printed our beam. So using a principal stress line field, we extracted some principal stress lines, and analyzing those, we could see we could generate compression, pure compression, theoretical pure compression, and pure tension lines that we used to print as our toolpath, but also to insert pre-bent rebars in the tension area. And here you can see how we went from a linear finite element to getting and selecting principal stress lines, how those became layers, and how then we adapted the speed, again, looking at the finite element analysis and at the fabrication constraints. And here again, this is a printed specimen. We tested a few of those, and we kept one for the pictures. And here we achieved 120% increase in strength to weight ratio compared to the full printed beam. And then the last step, I have a short video, and in this case we on top of applying this porosity in the longitudinal section, we also given the case of a point load in the center, we also optimize the shape, so the external profile of our beam. And then the rest of the process is similar to the previous elements. And here you can see how our digital workflow went from designing the profile of the elements to selecting the stress lines and using those to create a toolpath, and then reaching the point where we fabricated. And this allowed us to avoid any moment where we had to discretize our geometry. So we didn't go through meshes, but we went directly from our curves, from our stress lines to the toolpath and the fabrication process. And here again, the result, looking at only at the strength to weight ratio, we achieved the 200% increase compared to the first full beam. And then the next step was trying to apply and to challenge our workflow and apply to a slab element. So in the same fashion, we extracted our stress lines, in this case moment lines. We selected them looking at volume to deflection. So we did a range of options, and we looked at what was printable and what gave us the best balance between volume and deflection. And then we designed the depth of our ribbed slab. This slab is 3.5 meter length and 1.6 meters in width, and it's supported in 2 points. And the load case includes a distributed load as well as a point load in the center. And so we described the height using height maps, as well as we then work using to reduce the shear especially to reduce the shear in the support. We also increase the width of our layers. And this translated directly into motion speeds for our robot so that we could achieve the pre-planned heights and widths. And also here we integrated different sets of rebars, and the process of including rebars cannot be shown because it was done manually while printing most of the times. But what we also had to do here was to program the robot to print non-planar, because our ribs are not the thickness of our slab is not always equal, but it's varying. So we had to work on our toolpath so that we could achieve this by having variable layer height, and to, as Alessandro was showing earlier, to optimize the placement of the material by being always perpendicular to the previous layer. And again, a couple of these elements were tested here following Eurocodes, and we could see there was there was no visible deflection with the distributed load, and then we could achieve a breaking point only by loading it with our hydraulic press in its center. And this is the element that we printed. And so as an outlook to my research, what we understood is that using toolpath-based design allows a direct transition to optimize the manufacturing process. And at the same time, we could see how weight reduction equals, in a way, carbon optimization. And again, this can be done through shape optimization, but also through toolpath optimization, so optimizing the fabrication process itself. And in this sense, also having a high resolution control, even in such a large printing process, can help controlling the printing and improving the printing and its performance. And what we also saw, and what I also feel like it's very crucial for these processes, is to streamline more and more design to engineering and fabrication, I would add to this, workflows to be able to work between these three processes in a more integrated way. And then what's next in this sense is to bring this from lab to construction. And of course that entails a lot of things, but firstly is to try to understand how to make the process more consistent. And the second thing is to look at codes, and both how we can comply to those codes, but also how we can challenge and make these codes comply to what we are doing, and to have ways of validating what we are doing that can be embedded in new codes. And of course, looking at sustainable material alternatives, it's key to make extrusion 3D printing better, concrete printing in general, and concrete construction more sustainable. And then, of course, looking at improving design, engineering, and manufacturing processes from an environmental, an economic, but also a social point of view. Thank you very much.
To learn more about the CDFAM Computational Design Symposium series, to see the archives of previous presentations, and to learn about future events, visit cdfam.com.